Dear students of English version of class 11 of B.Sc, I am with you, Choetian, JICA Japan Certified Engineer, and Mizanur Rahman, Industrial Expert, Bangladesh Plastic Sector, Senior Instructor and Trainer, Bangladesh Institute of Plastic Engineering and Technology. Today, I will start the chapter number 2, Vector, from physics perspective. Before starting the chapter Vector, we should know one thing: what is physical quantity? In SSC, you have learned the physical quantity. In spite of it, I want to memorize you and explain a little bit what is physical quantity. Anything that can be measured in the physical world is called the physical quantity, or we can say the physical quantity is a property of a material or a system that can be quantified by measurement is called physical quantity. For example, length, velocity, work, speed, etc. That is, whatever we can measure, whatever is possible to measure, and whatever we have learned to measure is physical quantity. According to the structure, the physical quantities are classified into two types, into two categories. Number one, fundamental quantities. Number two, derived quantities. Now we see what is fundamental quantity. The physical quantities that are independent, neutral, that is, the physical quantities that do not depend on other quantities, rather the other quantities depend on them, are called fundamental quantities. For example, length, mass, time, temperature, electric current, amount of substance, luminous intensity, now we see what is derived quantity. The physical quantities that are obtained from fundamental quantities, that is, the physical quantities that are derived by the multiplication of fundamental quantities, are called derived quantities. For example, velocity, acceleration, area, volume, etc. Again, based on the directions, the physical quantities are classified into three types, into three categories. Number one, scalar quantity. Number two, vector quantity. Number three, tensor quantity. Now we see what is scalar quantity. In the book of Dr. Amir Hussain Khan sir, the definition is the physical quantities that have only magnitude, no direction, are called scalar quantities. In the book of Dr. Shahjahan Tapon, sir, the definition is the physical quantities that require only magnitude, no direction, to be represented fully, to be expressed fully, are called scalar quantities. In this definition, it is not mentioned here what is the way to represent. We can represent anything in three ways: by language, by mathematics, and by body language. So, to make more specific the definition, I will add a word mathematically. So, the definition is now the physical quantities that require only magnitude, no direction, to be represented mathematically are called scalar quantities. For example, length, mass, temperature, etc. To represent a scalar quantity, just need a single number with a unit and a mathematical sign. We see, for example, length, suppose 10 meter. Here, to represent length, it requires one number 10, one unit meter, and a mathematical sign plus, which is in the left of the number 10. Mass, suppose 15 kg. To represent mass, it requires a number 15, a unit kg, and a mathematical sign plus, that is in the left of number 15. Temperature, suppose minus 25 degree Celsius. Here, to represent the temperature, it requires a number 25 and a unit degree Celsius and a mathematical sign minus, that is in the left of number 25. So we see, to represent a scalar quantity, it just need a single number, one unit, and a mathematical sign. When a scalar quantity is in one-dimensional space, in two-dimensional space, or in three-dimensional space, how many numbers are required to represent a scalar quantity? Already we have known it just needs a number. In spite of it, we can calculate the numbers required to represent a scalar quantity by a formula n to the power r. The formula is n to the power r. Here, r is rank or order, rank or order. What is rank? The rank is the number of direction of a physical quantity. Number of direction of a physical quantity. And n is the number of dimensions in case of a scalar quantity. The rank or order, that is number of direction, are equal to 0. When a scalar quantity is in one-dimensional space, how many number is required to represent the scalar quantity? When a scalar quantity is in one-dimensional space, then n equal to 1. How many numbers required to represent the physical quantity? Equal to n to the power r. Here n equal to 1, r equal to 0, that is equal to 1. A to the power 0 equal to 1, we have learnt in mathematics in the chapter exponent and logarithm. When a scalar quantity is in two-dimensional space, how many numbers required? When a scalar quantity is in a two-dimensional space, n equal to 2, numbers required to represent the scalar quantity equal to n to the power r equal to n is 2, r is 0 equal to 1. When a scalar quantity is in three-dimensional space, n equal to 3. So, the numbers required to represent the scalar quantity equal to n to the power r, that is 3 to the power 0 equal to 1. So, we see here in every cases, when a scalar quantity is in one-dimensional space, two-dimensional space, or in three-dimensional space, the numbers required to represent a scalar quantity always need a single number. Now we see what is vector quantity. In the book of Dr. Amir Hussain Khan sir, the physical quantities that have both magnitude and direction are called vector quantities. In the book of Dr. Shahjahan Tapan sir, the definition is the physical quantities that require both magnitude and direction to be represented fully are called vector quantities. In this definition, it is not mentioned what is the way to represent the vector quantity. Like previous, I will add a word mathematically in this definition. As a result, the definition will be more specific. So the definition is now the physical quantities that require both magnitude and direction to be represented mathematically are called vector quantities. For example, velocity, acceleration, displacement, etc. The vector quantity has a magnitude and one direction. The magnitude is a scalar quantity and it is always positive. How many numbers required to represent a vector quantity when it is in one-dimensional space, two-dimensional space, in three-dimensional space? We can calculate this by the formula n to the power r. Now we see n to the power r. Here for vector quantity r equal to 1. That is, the number of direction of vector quantity is 1. When a vector quantity is in one-dimensional space, n equal to 1, then the numbers required to represent the vector quantity equal to n to the power r equal to 1 to the power 1 equal to 1. When a vector quantity is in two-dimensional space, n equal to 2, numbers required to represent the vector quantity equal to n to the power r equal to n equal to 2, r equal to 1, 2 to the power 1 equal to 2. When a vector quantity is in three-dimensional space, then n equal to 3, then numbers required to represent the vector quantity equal to n to the power r equal to 3 to the power 1 equal to 3. So we see here in all the cases, that is in two-dimensional space, one-dimensional space, three-dimensional space, always different numbers are required as per the number of dimensions. Now we see why displacement is vector quantity. What is the definition of displacement? In a specific direction, the change of position of an object is called displacement. So, the displacement has a magnitude and a direction. According to the definition of vector quantity, the displacement is a vector quantity because in vector quantity there is a magnitude and a direction. Why velocity is vector quantity, acceleration is vector quantity, why force is vector quantity, why weight is vector quantity? We can show this by the definition or by the analysis. What is the definition of velocity? The rate of displacement with respect to time is called velocity. So, the velocity is a vector quantity because the displacement is a vector quantity. Also, we can show by analysis. Before analysis, we should know the rules of multiplication. Later on, I will discuss the rules of multiplication in details, but here you just see as a note the rules of multiplication. Number 1, scalar quantity. Scalar quantity multiplied by a scalar quantity equal to a scalar quantity. Why? The scalar quantity has only a magnitude. This scalar quantity has only a magnitude. If a magnitude is multiplied by another magnitude, the product will be a magnitude. That's why this is a scalar quantity. Number 2, vector quantity multiplied by a scalar quantity equal to vector quantity. Why? This is a vector quantity that has a magnitude and a direction. This is a scalar quantity that has only magnitude. If a magnitude and a direction is multiplied by another magnitude, the product will have a magnitude and a direction. That's why this is a vector quantity. Number 3, vector quantity dot multiplication vector quantity equal to a scalar quantity. Why? In the dot multiplication, the vector quantity has only magnitude. The vector quantity has only magnitude. That is, in the dot multiplication, the magnitude of a vector quantity and the magnitude of vector quantity is multiplied. That's why the product will be a magnitude. So it's a scalar quantity. Number 4, vector quantity cross multiplication vector quantity equal to vector quantity. Why? In this multiplication, the vector quantity has a magnitude and direction. The vector quantity has a magnitude and direction. If a magnitude and direction is multiplied by another magnitude and direction, the product will have also a magnitude and a direction. That's why this is a vector quantity. Now we see what happens in velocity. We know velocity equal to displacement divided by time equal to displacement multiplied by 1 by time. This is a vector quantity that has been already discussed. Vector multiplied by time is a scalar quantity. So 1 by time is a scalar quantity. If a vector quantity is multiplied by a scalar quantity, the product is a vector quantity. Because the vector quantity has a magnitude and a direction, and the scalar quantity has only magnitude. If a magnitude and direction is multiplied by another magnitude, the product will have a magnitude and direction. So this is a vector quantity. Now we see what is tensor quantity. The physical quantities that require multiple magnitudes and multiple directions to be represented mathematically are called tensor quantities. Or we can say the physical quantities that have different magnitudes and different directions but do not follow the rules of addition of vector, rather follow the rules of algebra, general algebra in addition, are called tensor quantities. For example, moment of inertia, stress, strain, conductivity, electromagnetism, etc. To represent tensor quantity, how many numbers are required, we can calculate by the formula n to the power r. N to the power r. Here r is rank or order, that is the number of direction of the physical quantity, that is number of direction of tensor quantity equal to greater than 1. Let r equal to 2. When a tensor quantity is in 3-dimensional space, how many numbers required? When a tensor quantity is in 3-dimensional space, n equal to 3, the numbers required equal to n to the power r. N equal to 3, r equal to 2, equal to 9. So, when a tensor quantity is in a 3-dimensional space, the numbers required is 9. Now we see why moment of inertia is tensor quantity. This is x, this is x-axis, this is y-axis. There is an object in this plane. The distance of m1 particle from y-axis is r1. The distance of particle m2 from y-axis is r2. The distance of m3 particle from y-axis is r3, and the distance of m4 particle from the y-axis is r4. If this object rotates with respect to y-axis, then the moment of inertia of m1 particle is I1 equal to m1 r1 square. The moment of inertia of m2 particle is I2 equal to m2 r2 square. The moment of inertia of m3 particle is I3 m3 r3 square. The moment of inertia of m4 particle is I4 equal to m4 r4 square. Here we see that the moment of inertia of M1, M2, M3 and M4 particle are different because the distance of M1 particle R1, the distance of M2 particle R2, the distance of M3 particle R3 and the distance of M4 particle R4 are different, and the mass of M1, M2, M3 and M4 particles may also different. That's why the magnitude of moment of inertia will be different. Directions may also different because the direction of M1, M2, M3 particles are different. So because of different magnitudes, because of different directions, moment of inertia is a tensor quantity. Tensor quantity. We see sometimes pressure is scalar quantity, sometimes pressure is tensor quantity. Now I explain this. Suppose this is a hydraulic cylinder. There is hydraulic oil inside the cylinder. One force F is applied on the top plane of the cylinder. That's why pressure is developed P equal to F divided by A. According to the Pascal's law, the pressure developed inside the cylinder is same, but the direction of acting pressure is different. The direction of pressure is different, like this, like this, like this, like this, like this. Direction of pressure is different, like this. The direction of acting pressure is different, like this. So the pressure has only a magnitude and the directions are different. So it is not vector quantity because the vector has only one magnitude and one direction, but here the pressure has a one magnitude and different directions. It is not also tensor quantity because the pressure has only one magnitude and the number of directions of acting pressure are different. So according to the definition of tensor quantity, tensor has different magnitudes and different directions. That's why it is not tensor quantity. Now the pressure has one magnitude and the number of directions is different. That is, the pressure is acting all the directions. That is, in 360 degree the pressure is acting. If a system is acting in 360 degree in every directions, in that case it is no need to mention the direction. It is enough to mention the magnitude. That's why it is a scalar quantity. The pressure is a scalar quantity. Now we see what happens in gas. Suppose This is a gas cylinder. There is gas inside the cylinder. This type of cylinder we use in our home, in kitchen, to cook food. There is pressure inside the gas cylinder. According to the Pascal's law, in case of gas, the pressure is the same in all the points, in every points inside the cylinder. So the pressure has only one magnitude, but the pressure is acting in these directions, in these directions, in these directions, in these directions, these directions. In the gas cylinder, the pressure has only one magnitude, but the directions are different. So it is not a vector quantity. Vector quantity. It is also not a tensor quantity, because the vector quantity has only one magnitude and one direction, but the magnitude is same, but the directions are different. The tensor quantity has different magnitudes and different directions. If a system acts on all the directions, if a property acts on all the directions, that is, the property acts in 360 degree. In that case, it is no need to mention the direction. It is enough to mention the magnitude only. So it is a scalar quantity. Now we see when pressure is tensor quantity. Suppose this is a solid substance or this is a solid plane. Force F is acting on it. As a result, pressure is developed, P equal to F divided by A. In this case, the magnitude of pressure decreases gradually from here. The magnitude of pressure is decreasing gradually from the line of action of force, and also the magnitude of pressure is decreasing layer to layer. Magnitude of pressure is decreasing layer to layer, and the directions of acting pressure may different. Since the developed pressure have different magnitudes and different directions, that's why in this case, in solid substance, in solid plane, or in a solid object, the pressure is tensor quantity. Tensor quantity. Now we see we have learned three types of physical quantities, that is scalar quantity, vector quantity, and tensor quantities. But there are two types of physical quantities in your books, scalar quantity and vector quantity. If there is no option of tensor quantity in exam, in MCQ question, then by closing your eyes you will take the tensor quantity as a scalar quantity because tensor quantity is not vector quantity, and also tensor quantity follow the addition rules of general algebra like scalar quantity. So in that case, you will take the tensor quantity as scalar quantity. Now I make a summary upon the discussions today. The scalar quantity has only one magnitude and no direction, that is number of direction is 0. The vector quantity has only one magnitude and a direction, and the tensor quantity have different magnitudes and different direction, that is multiple directions and multiple magnitudes. This is the ending of today. See you in the next class. Thanks to everybody. Thanks to all.